a base plate of an iron. So consider a base plate of household iron is 1200 watts, and thickness of the iron is 0.5 centimeter, and area also given 300 centimeter square, and thermal conductivity of the iron given also 15 watt per meter degree Celsius. Now the inner surface of the base plate is related to uniform heat flux by the resistance heater inside. So this on the resistance heater inside, and this heater heat is generated will be generated heat flux for through the plate. Now outer surface, this iron plate outer surface loss heat surrounding at a 20 degrees Celsius. So your surrounding temperature is given as a 20 degrees Celsius by the convection. Now here also convection coefficient is given for the surrounding is H given as 80 watt per meter degree Celsius. Now also we can, here's another consideration given, we can ignore the heat loss by the radiation. So here will be heat loss related to conduction throughout the plate, and plate to the surrounding will be related to convection. Now find out the expression of variation of temperature in the base plate. Also evaluate the temperature at inner surface of the base plate and outer surface of the base plate. Okay, first we'll write down the given parameters. So here given, say given, say Q is given 1200 watt, and thickness of the plate given 0.5 centimeters. So we'll convert to the meter, so divided by 100, so 0.005 meter. Then area given is a 300 centimeter square, so we'll convert to the meter square, so 300 times 10 to the power -4 meter square. Thermal conductivity K for the base plate given 15 watt per meter degree Celsius, and surrounding temperature is given 20 degrees Celsius, and convection heat coefficient given 80 watt per meter square degree Celsius. Okay, so these are the given parameters. So here main important assumption is there's insulator on the top of the iron. So upper part of the iron is well insulated, so that the interior heat generated in the resistance wire, so here this resistance wire will pass through the only the base plate, so only through this way. So heat will transfer only through in this way. So that means it will be steady state condition, and there's another consideration given, there is no radiation heat transfer. So if I divide into two parts, so this one is our upper portion of the iron, and this on the base plate. So this heat will transfer through only this direction, and in a question is given is a uniform heat flux generated by the resistance will transfer through the base plate. So uniform heat flux will define with the Q double prime, so it will be it will be equal to your heat transfer divided by area of the base plate. And we can consider this one will be the heat transfer through the only one dimension. So if you can say this one is x, say this one is 0 0 location, x is 0 here, and here is a thickness L, so thickness given 0.5 centimeter. Okay, so first now there is a details formula related to rectangular coordinates. So this our problem is related to rectangular coordinates. So these are the general heat conduction equation. So first part related to heat flow through the x-axis, this one for y-axis, this one for z-axis, and this one is your heat generated, and right hand side part is the if temperature vary with the time, so for unsteady condition. Now if there is a case is a k is constant, so formula will become this one. And if the for the steady state condition, your right hand side will become 0 because t will be constant. It will not depend vary with the time. Now our problem is related to steady state, also one dimensional. Heat will flow through the only in x direction. So you know heat will flow from the y-axis, no heat will flow from the z-axis. Also there is a no heat generation, so this part will become 0. Also this one is steady state, so right hand side already 0. So our equation will become only for the first portion for one dimensional steady state with no heat generation. This one is in this problem our k also constant, so we can write down differential equation. Heat transfer through the plate will be d square t over ds square equal to 0. So this on the one dimensional heat conduction differential equation. Okay, now for general solution, if we will integrate this one, say equation 1, we will integrate equation 1 2 times. So for the general solution, so integration twice. So if you integrate twice equation 1, after first integration it will become dt over dx equal to c1. C1 is the constant, integration constant. So again if you integrate this one, it will become t function of x, so c1x plus another new parameter c2 for the second time integration. Say this one equation 2, this one equation 3. Okay, now here C1, Ct is the constant. We'll find out this too. Now we will use the boundary condition. So boundary condition, so boundary conditions. So we need minimum 2 boundary conditions. Say when x equal to 0. Say x equal to 0. Say here is x equal to 0. So heat flux is uniform. Is question given as a uniform heat flux. Is a uniform heat flux. So we can write down when x equal to 0. So heat flux equal to negative k area. No, sorry, heat flux, so no area. So d dt at x equal to 0 over dx. Okay, now from equation 2, if we use the equation 2 here with this boundary condition, we can write down heat flux will be equal to minus K C1. So C1 will be this portion, the dt over dx from equation 2. So from equation 2 equal negative K C1. So our C1 will be negative heat flux divided by heat conduction. Okay, so another boundary condition, say when x equal to L at the outer surface, so outer surface heat flux also equal to minus K dt over dx, so at x equal to L. Okay, now for outer surface, x equal to L means at the outer surface. So outer surface heat flux will be related to the convection. Inner surface here for the x equal to 0 was here, heat flux was related to conduction. And heat flux will flow through this as a heat flux. Throw in this way. So convection heat flux. So heat flux convection, we know the formula is convection coefficient, then surrounding temperature, sorry, the surface temperature minus the surrounding temperature. So here at point here, this surrounding temperature we can find out from our equation 3 from here. So if you put x as L, we'll get the surrounding temperature as XL. So we'll use here. So here our heat flux will be related to convection. So temperature at L minus surrounding temperature, and right hand side is K, and dt over dx same as C1. So if you use the equation number 2, so dt over dx equal to C1. So we can write down here for this portion as a C1. Okay, so now for this one, t at point x equal to L, so we'll use the equation 3. We'll use this equation and we'll use here x equal to L. So it will give us the temperature at when x equal to L. So if you use equation 3 and if you put x as L, so we can write down, say, from equation 3. So it will become, say here, so C1 L plus C2 and minus T alpha as it is. So this portion from the equation 3 equal to minus K C1. So we can expand this one, say H C1L plus AC2 minus ST alpha equal to minus K C1. So we'll find out the C2. So we'll keep the C2 in our left hand side. AC2 equal to, everything will bring, rest of remaining part will bring the right hand side. So it will be, say, this one negative. If you change the side, will become positive, say this one already in the right hand side, so it will remain negative C1, and remaining part, this one will be negative convection coefficient, then C1 length. Okay, now we can write down C2. This one is C2 equal to, if we divide it by H, it will become T alpha minus K over H C1 minus C1L. Okay, now we'll use the C1 value. So here C1 value is flux divided by negative flux divided by heat conduction. So T alpha minus K over H heat flux negative and divided by K. Also here C1 is negative. We're using the C1 value. So it will become negative, negative will become positive, K will cross out, so positive heat flux divided by convection coefficient, negative, negative, this will also become positive, then say heat flux divided by K and the length. So we got the C2 value also. Now we will put C1 and C2 value in the equation 3. So equation 3 was this one. So it will become, if T x C1 is here, negative heat flux divided by K, then the x plus C2 value. So C2 from our last calculation will be T alpha plus heat flux plus heat conduction and length. So we can simplify more, say T alpha plus heat flux K L minus X plus 1 over S. So it will be our temperature variation throughout the iron plate. Now we can calculate any point between inner surface to outer surface temperature. So this is our first answer. Now question also mention, so evaluate the temperature in inner surface and outer surface. That means find out the temperature at when x equal to 0 and when x equal to L. Okay, now we'll find out the temperature. So this one is our temperature variation formula. If we write down again at the bottom, say temperature distribution or variation at any point from inner surface to outer surface will be T alpha plus Q prime and L minus X K. I just copying the word solution. Okay, now here this Q you can write down Qx because heat will transfer through only the one axis, and so here we consider in the x-axis, so you can write down Ux because this is an one-dimensional problems. It will throw to the only one direction, so you can write down Ex, or is fine if you don't want to write down. Oh, it what happened? Yeah, say Ux. I try to keep the same as your view solution, so it will be Qx. Okay, so now we have the distribution temperature distribution equation. Now we'll find out for inner surface. So inner surface temperature, say T when x equal to 0 equal to surrounding temperature is 20 degrees given. So 20 degree plus heat flux we didn't calculate yet, but is a heat transfer given, we can calculate here in separately. Say heat flux will be your Q divided by base plate area. So Q is given 1200 watt per meter, sorry, watt, and area is given 300 centimeter square. So we'll convert to the meter square. So it will be 4 times 10 to the power 4 meter square. Sorry, watt per, it will be watt per meter square. So watt per meter square. Okay, so Q is 4 times 10 to the power positive 4. Now here length means thickness of the plate is given 0.5 centimeter. So 0.5 centimeter divided by 100, it will become meter. So 0.005 minus x. Now we calculate the inner surface. So x equal to 0 divided by k, and k given thermal conductivity given 15 plus 1 over convection coefficient given 80. Now if we solve this one, we'll get the temperature at inner surface. So when x equal to 0, so it will be 533 degrees Celsius. So temperature at inner surface. Okay, now we'll also calculate the temperature at the outer surface. So that means when x equal to L. So when x equal to L, so temperature will be 20, same formula. Now we'll use x as L plus heat flux. So 4 times 10 to the power 4. Now L minus x also L. So divided by k, so it will become 0 plus 1 over 80. So 80 is the your convection coefficient, heat coefficient. So result will be 520 degrees Celsius. So this one is our last answer, is a temperature at outer surface. Okay, so this was all about our question one. So at the beginning, we consider some assumption, then we select our general heat conduction equation for the steady state one-dimensional with no heat generation, this formula. Then we integrate twice to find out the general solution for this differential equation. Then there is a two integration constant C1, C2. We solve these two from the two boundary condition at when x equal to 0. We use the uniform heat flux condition, and x equal to 0 heat flux only was related to conduction, and when x equal to L means in outer surface, heat flux was related to convection because heat will loss from plate to the air by the convection. Then we use the convection heat flux formula. Then we solve two equation number 2 and 3 to calculate the C1 C2. Then we use this C1 C2 value in our general distribution equation in equation 3. Then it will become only related to temperature and the distance and heat flux. Then we calculate the based on this equation. Now then we calculate the heat temperature in inner surface means when x equal to 0. Also we calculate temperature at outer surface means when x equal to L. Okay, now if you have any question related to this problem, so we will discuss in our tutorial schedule times. In tutorial schedule times, it will be the answer and question and answer session related to this tutorial video. Okay, now I will show you how to solve the question number 2.